Welcome, or hopefully welcome back to the Reliability Matters podcast, the podcast where we explore the tools, techniques, and best practices to ensure reliable electronic assemblies. This is episode number 163. I'm your host, Mike Conrad, and today we're diving into the critical yet sometimes overlooked component that powers so many of the devices we rely on: batteries. Batteries are the heartbeat of countless electronic products, from medical devices and electronic vehicles to consumer gadgets and industrial systems. Choosing the right battery is not a one-size-fits-all decision. It requires a keen understanding of the application, performance needs, and environmental demands. The right selection can make the difference between a product that excels in reliability and one that quite literally fails to deliver. But there's more to batteries than just selecting the right chemistry or capacity. Safety is paramount. Poor battery selection, design, or management can lead to performance issues, overheating, or catastrophic failures. As we've all seen in headlines, battery malfunctions can result in recalls, damage to brand reputation, or worse, safety hazards for users. To shed light on this vital topic, we're joined by an expert in the field of battery technology. Alex Norman is a battery management system designer at Pro Technologies, a well-established and trusted custom battery pack manufacturer providing engineering capabilities from concept through production. Their leading-edge manufacturing facility and headquarters is based in Pilot Mountain, North Carolina. Alex has deep experience in printed circuit board design, product development, battery management systems, and more. Alex is also a content creator, focusing mostly on electronics, battery, and battery management systems content available on his LinkedIn page and his YouTube channel. Today, we're going to explore how to choose the right battery for your assembly, best practices for integration, and how to mitigate potential safety risks. So, if you care about keeping your products powered, reliable, and safe, don't bolt just yet. This podcast on batteries is positively charged with insights. Stick around and top off your battery knowledge.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Well, were there enough puns in there for you, Alex?
I did enjoy the puns. I did.
I saw you laughing there. I also saw you kind of grooving a little bit to the music. So I think we're going to have some fun. Thanks for agreeing to be my guest on this program. I really appreciate it.
Yes, thank you for inviting me. I am excited about being on the program.
Well, I saw quite a bit of your work. You do a lot of content creation, largely on the subject of batteries, but not exclusively on the subject of batteries. There's a PCB assembly stuff in there, design stuff in there too, as far as I remember. Battery tech has always interested me, particularly in modern times. You know, batteries are getting kind of a bad rap lately, maybe deserved, but they're certainly getting a bad reputation. And I think the first time that came to the forefront of my mind was with Samsung phones. And there was a time when I remember, I fly a lot. I do a lot of speaking around the world, and I spend a lot of time on airplanes. And I remember a whole era where, in addition to fasten your seatbelt and put your tray table, stow your tray table and clear the aisle, it was if you have a Samsung phone, get off the plane, basically. Yep. By specifically Samsung phones, and they even had the model, whatever the model was. And then, of course, with EVs, we've seen some examples, well-publicized examples of spontaneous combustion and things like that. And I have some friends who are firefighters, and they've told me how dangerous battery fires are because they burn exceptionally hot and they're ferocious and they're very difficult to put out. And every time I check into an airplane, when at the ticket counter, when I'm checking in, they always ask you, do you have any bombs or firearms or batteries? And they don't allow batteries in check bags, and you can carry them on, but you can't put them in check bags. And then I started thinking, wait a minute, at any given time, there's a battery in my back pocket when I'm walking around,
Yep.
in my
Yes, there
phone.
is.
And if I'm listening to my AirPods, there's batteries in my ear, quarter inch away from my brain. And then, for some people, there's batteries in their body, maybe a defibrillator or a pacemaker, or, some medical device. So batteries are ubiquitous these days. And safety is certainly something we're going to get into. But before we do, let's talk about the content that you create through your
Okay.
YouTube channel and LinkedIn and all of that. What made you decide to start sharing your knowledge with the world and create a show?
Well, I've been posting on LinkedIn for a good few years now, and then I started actually gaining traction. I was just posting little bits of things here and there, maybe once or twice a month, something like that. And then it started to gain traction. I started to gain followers. And so I thought I might as well make some content about the things I do here at Pro Technologies and see if people would enjoy that. And it just sort of grew into this thing that it is now. There was really no intent behind it. It just kind of happened, I guess, is the truth.
Yeah, and I find it's a little bit like quicksand. The more content you make, the more you make.
Mm-hmm.
Meaning you just make more, and then you start getting comments, and people want to hear certain subjects. Does some of your content is some of your content a result of your viewers asking for specific types of content, or what inspires
a lot
you?
of it is.
Yeah.
A lot of it is. So a lot of people want to hear about BMS content and batteries and those type of things. That's why that's my main subject, because there's not really any battery content out there. Most people treat batteries as some kind of voodoo that you have to go see a witch doctor to learn about or something. But
Right.
that is mainly what people want to see. So that is the content that I enjoy making, and then PCB design content and those kind of things.
Well, it's funny because everyone's familiar with batteries, but we're scratching the surface. I think we're all familiar with batteries because we all use batteries, pretty much daily. And but you're right, very few of us know the tech behind a battery. It's not just lead and acid anymore. It's quite complicated. Let's dive into some battery tech. Help me understand some of the key differences between the types of batteries. I am by no means a battery expert, but I'm familiar with a few of the acronyms, like lithium-ion batteries and nickel-metal hydride batteries, and of course lead-acid batteries and alkaline batteries. I don't know if they're just a fancy version of lead-acid or not, but what are the differences between these types and other types of batteries, and in terms of performance and reliability and capacity, things like that?
Well, the highest performing batteries are going to be anything that's lithium-based, right? But anything that's lithium-based is going to be the most volatile or the most unsafe. So things like alkaline batteries, like your double A's and triple A's that go in your remotes and all the kids' toys and things, those are non-rechargeable, the safest you can get. They're nominally 1.5 volts, maybe 1 or 2 amp hours. They're about the most common battery you can get. And then the nickel metal hydride, those were some of the first rechargeable batteries, portable batteries. They were made as kind of a drop-in replacement for alkaline. So they're a little bit less energy dense than alkaline, but again, they're safe. Well, they're safe according to the regulatory agencies. I'll give you a little secret, a little industry secret here. Nickel metal hydride batteries before lithium-ion came out used to be treated like lithium-ion is now in the safety industry. That they had regulations around it and all these things. And then when lithium-ion came out, they marked nickel metal hydride as safe. But nickel metal hydride batteries, if they are to vent, they put out hydrogen gas, and hydrogen gas is flammable.
Yes, it is.
So it's
funny. It's safe by comparison.
It is safe by comparison.
I call that the ugly waitress or ugly waiter theory. When someone complains about their food, they hold it up to their face and go, "Well, how does it look now?" Right.
Yeah.
So I guess nickel metal hydride batteries is a how does it look now? Now that we have something that's even more dangerous. I'm sure the people who manufacture those were like, "Whew," the attention's gone somewhere else. I've heard a lot of talk recently. In fact, I had someone on my show who's in the EV world. He's an expert in the EV world, and that, of course, involves batteries and battery management systems and chargers and things like that. And there's talk about trying to improve the technology behind sodium-ion batteries. Basically lithium-ions without the dirty lithium stuff. And and even the United States has supplies of sodium. Right? We don't have to go to other countries and have children dig it up by their fingernails. And it's safer, but it's not as effective. It's not as good. Have you heard talk about sodium-ion batteries as maybe a possible replacement?
Yeah, sodium-ion is getting very popular for large format batteries because you can replace the lithium with sodium, because sodium is actually in the same category on the periodic table as lithium is. And so the problem with sodium-ion is it's so much less energy dense.
Right.
So for your physical size, you're about half the energy density than lithium-ion would be. And then you're 20%, 10 to 20% less than lithium iron phosphate would be at the same size. So that is the major problem with sodium ion. And then the process hasn't quite been worked out to where it's more economically viable to do sodium ion, even though sodium is much more abundant and cheaper than lithium is. But the industry is definitely trending toward those type of batteries because it's replacement for lithium. But don't be fooled, because 90% of the battery market is still lithium-ion NMC cells. That is still 90% of the market as of today. So any technologies are very slow moving to replace any of that.
Yeah, they're just waiting for the next evolution or maybe even revolution in battery technology to come along before they replace it. I guess to your point about energy density, if it's a large form factor and weight's not an issue, then they could go with maybe a less dense battery, array of battery packs and get the total amount of energy they need. But if it has to fit in a Tesla or you blow the floorboards of a car, where you have a fixed dimension between the wheelbase, that's an issue.
Well, safety is the major draw for that. So the more lithium ion cells you put together, the bigger the fire is going to be, right? And so lithium iron phosphate was a good replacement for that, because lithium iron phosphate doesn't go into thermal runaway like lithium ion does. And now sodium ion has come on the market, which is the same safety level as like a lithium iron phosphate would be, but it's cheaper to produce. So now all of your large format for, almost the same energy density could now move to that. Cheaper, it's just as safe, and all of those things. So that is really the draw with a chemistry like that, is the safety, because lithium ion is extremely volatile if it's not treated properly.
I had read some time ago, I think it was in the context of the Samsung phones that were catching fire, that one of the primary causes, or at least it was written about, was dendritic growth within the battery cells, caused by some type of foreign object debris or residue or some imperfection in the manufacturing process. Is that your understanding as well?
Yes, or it can be caused by abuse as well. So
stupid human tricks. Stupid human tricks, right?
So there is a range. There's a window that a battery likes to be in, right? And so for a lithium-ion cell, peak charge is 4.2 volts. Your end of discharge is 2.5 volts. If you charge it up too much, you can drive it into where it gets too hot, and then it'll catch fire. It'll heat up too much. But if you drive it too low, or you get it too hot, too cold, those kind of things, it damages the internals of the cell and causes dendrite growth. And so if you bring it down to too low of a voltage and then you charge it back up and those kind of things, that causes dendrite growth. And then that dendrite will grow through the separation layer in between the two electrodes. It'll grow between the separation layer and then cause an internal short and thermal runaway.
Interesting. I was amazed to learn when EVs kind of hit the market that the battery, when you look at pictures of how EVs are made, you see the battery platform. But that's just the casing. Inside, it's hundreds or thousands of cells. Like someone just went out to the store, went to Amazon and bought 5,000 double A's or something. I don't mean literally, but and then just put them all in series or something. I mean, that's and I know that the wording on your company's website says you're a manufacturer of battery packs, which tells me that that it's just a question of how many cells and what types of cells are required for the application, right? So we don't make batteries that are the size that would go in an EV as a one single battery. They're just, I think it's several thousand cells or something to that effect. It's quite dramatic. How has battery technology evolved in the last decade or so, or maybe even in the last 10 minutes since we started talking? What are the innovations that you see maybe that are even on the horizon? So where have we come in the last 10 years, and where do you think we're going in the next 10?
Well, the sodium-ion batteries is one of the biggest, because using a non-rare earth substance to create a battery is pretty. That's a pretty big leap in technology. So you no longer need lead or nickel or lithium. You can create it from a non-rare earth substance. So that's pretty good. That is your major metal, right? And but the biggest thing really on the horizon now is solid state batteries. I don't know if you've read anything about solid state batteries, but it uses a solid electrolyte instead of a liquid electrolyte. Now, solid state batteries have been around for a few years. A lot of wearable devices or like pacemakers and stuff, a lot of those have solid state batteries, have solid electrolytes. But they figured out how to make them in extremely large format. So the way those work, since they have a solid internal, then it's surface area based. So the bigger you can make the battery, the more capacity that you have. And they're working on right now, I know Toyota's working on one, and some of the other people are working on one, these large format batteries to go into electric vehicles that will just be these large single panel, or maybe stacked on top of each other panel of batteries. And the thing that is cool about solid state batteries is if they're punctured or if they're cut or those kind of things, they won't react to it. They're perfectly safe from most damage. A few years back, they had at the battery show, they had a guy who presented, and he showed a video of them taking a weapon and shooting holes through one, and it was still just sitting there, just a pumping away. It didn't care. So they already work on the small scale, but getting the amp hours up and those kind of things are what they're working on right now. And then they'll eventually be very large format solid state batteries. I don't think there will ever be an application for high use portable devices like your phone and things that require so much power. But definitely for like EVs and stuff, once you get to that scale, it is certainly going to be a viable solution and a lot safer of a solution.
Yeah, I think I realized that batteries have a liquid electrolyte or liquid material in it two ways. One is when you don't change, in a consumer device, you don't change the battery for a great deal of time, and then you find the device and you go to run it and you realize it's not working, and then you go to change the batteries and it's all corroded. They leak out, right? And that material that leaks out is probably pretty acidic or caustic. I'm not sure what side of the scale it's on, but it eats up your device. And the other was kind of in some cell phone form factors, they use almost like pouches, which are the batteries. They're a soft packaged battery so that they could mold around other components in the casing. So, yeah, solid state would seem a little better from a consumer standpoint because you don't have to worry about the worst thing that would happen is if you never change your battery is it just wouldn't work anymore. You wouldn't have to worry about it leaking and destroying whatever it's supposed to power.
Have you ever seen a cell phone that is swelled up?
Yes.
From the lithium battery in the back, swelling up. That's because it's a pouch cell. It's a lithium polymer. So lithium batteries do that. But when you have a cell like an 18650 that's metal cased, it can hold that pressure. But a polymer can't because it just has that aluminum shroud around it. And so they'll swell up.
It's a little scary to think that at any given time in my back pocket, there's a battery that's under pressure, and
Oh yes.
if that pressure releases, certain components of that battery can mix that aren't supposed to mix and light your back end on fire pretty quickly. Although I don't think I've heard of that happening, but it certainly theoretically could.
It's something that people don't realize. Now, when you were talking about the Samsung phones, I have a Samsung phone. I remember, I think those were the Galaxy S7s.
Yeah, I know there was an S in there. Yeah.
And so like on my cell phone, I carry an S23, and it has a feature that is called short charging. So you can set it to where it'll only charge up to 80%. So that way you're never getting to the top end of the charger, never topping off the battery. That extends your battery life and then helps it be just a little bit more safe than it would be.
Yeah, I've noticed on my MacBook Pro, which I'm staring at right now, if I keep it on the charger, which I do, I use it all day long, so it's always charging, it will settle at 80%, and then it'll put it on deferred charging. It won't actually start charging again until it drops below 80%. Its battery management software likes the 80% number. And, sometimes I'll freak out. The first time I noticed that, and it didn't happen when it was new. It happens as the computers age a little bit, the batteries age a little bit. The software will optimize charging and optimize battery life, I should say. And it'll only charge it up to 80%. And you can override that. You can just say, hey, charge anyway. But yeah, there seems to be a whole technique. When I was younger, I remember, I think it's when Alkalines first came out. Or no, it was when rechargeable batteries that fit into like AA and AAA formats first came out. There was this whole, I don't know if it was just a urban myth, urban legend, or if it was real. There was a way to, what's the good word? To prepare the battery for its life. And one of them was let it get all the way down, drain it completely, and then recharge it before you use it, in something that you need to use it for. It was like preconditioning your battery before. And consumers were told this. I remember reading that in some instruction. Don't take it out of the box and just charge it back up to 100%, based on what it's lost during shipping. Drain it completely, then recharge it. And I have a couple of electric bikes, and they gave some similar instructions. Don't top it off. Try and use it to as near zero as possible, and then make sure that every experience for the battery on a charger is as much of a full charge as possible, because I think the word they use is batteries have a memory. And if it's always used to being charged from 80 to 100, it will lose some of its capacity. Is that accurate?
Well, the reason we would do something like that is so that way the battery management system would cycle. So most of the BMSs we developed are smart, so they can learn the cell stack that they're on. Each cell has its own, different internal impedance and things. They're all relatively the same, if per cell model. But the reason you take it all the way down and charge it all the way back up is so it can figure out how much capacity is in its cell stack. How much it can discharge and all of those kind of things. And it kind of figures that out so it can give you an estimated state of charge.
Interesting. And on the subject of battery management systems, and I know that's the playground you work in regularly, what role, besides maybe extending battery life, but what other roles do battery management systems play in enhancing the performance and the reliability of a battery?
Oh man, you've picked my favorite subject. This is all I do. So a battery management system does just that. It manages the battery pack. So like a lithium-ion cell, which is or a lithium iron phosphate cell, which is what you mostly need a battery management system for. They have a charge window, a discharge window, a maximum discharge rate, and then a maximum temperature spec. And so what the battery management system does, it ensures that the battery pack stays within, this happy window. It has to stay here. If it gets too much voltage, it overcharges, then it has either, for small battery packs, it has a set of FETs, output FETs. So it cuts the output off, whether there's charge coming in or there's discharge coming out, it can cut the output off. So too much charge coming in cuts the output off. If it has too overcurrent and discharge, if it has a short circuit, whatever, it cuts the output off. Over temperature cuts the output off. That is what the battery management system's purpose is to protect the battery and keep it inside of its, its happy window. And the problem, which the reason I did a series, or I'm doing a series on my YouTube channel about this, is the problem is people just they'll buy a battery management system or a BMS off of Amazon or Alibaba or one of those kind of things and just throw it on a pack. They DIY'd it themselves and suddenly it's safe. And it's not safe at all, because those have to be set up for your specific cells, your specific amp hours, discharge rates, and all of those kind of things. So just because, an 18650 cell is the same size as another one, I'll give you an example. We use two different types of cells. We use power cells, and we use capacity cells. There are two different types of cells. One can do high current. Like, for instance, we use a lot of the Moly P26As. They can do, I think, 25 to 30 amps peak discharge. That's a lot of current out of a battery. Or we use capacity cells. And so those have more capacity but can't do as much output current. They can do around 10 amps. So you can't just slap those in and exchange them if your device pulls 20 amps. So that's where a BMS comes in handy. It keeps a battery pack in its happy place. Just like we like to be in our happy place, it keeps the battery packs in its happy place.
Yeah, interesting. Can you explain the difference? And this is a legitimate question because I've heard the phrase used before, and I don't quite understand how it applies to battery technology, but the difference between primary and secondary batteries and when each type is most appropriate.
Yeah. So primary is single use. So I don't know if you've ever used any flashlights like an O-light flashlight that uses a DO 2/3 type of cell. That's a lithium primary pack. It's a one use and done. Whereas a secondary battery or a rechargeable battery is made to be used over and over again. And so I think most of them are lithium thionyl chloride, I believe, is what most lithium primaries are. I didn't have that written in my notes, but like a DO 2/3, they're made to hold their capacity, made to be shelf stable, made to be safe, and then they're single use. Whereas like a lithium-ion cell, since it's meant to be rechargeable, it will actually lose about 1% of capacity a month. You just leave it on the shelf, leave it for 12 months, it'll be 12% down. Just a little side note, if you have a device with a lithium-ion battery in it, you shouldn't just leave it on the shelf for a few years. Probably is in there growing dendrites.
Right. So the longer, but if it's in use, that phenomenon doesn't occur. This is when they're just sitting on a shelf not being used. Mm-hmm. Is that when the bad actors kind of come out and play?
Yes, because eventually the cell will discharge, especially if you got done with it and it's dead, and then you just go and set it on the shelf. Then it will continue to just self-discharge, right? Until the point where you go and it's completely dead. It has 0 volts on it, and then that's when damage occurs. So if you have a lithium cell that's got 0 volts, I would not charge it back up.
So it's the charging back up because of its damaged state that can be problematic.
Mm-hmm. That can be problematic.
Yeah. Wow. I'll have to go through and see what I have. How come, this is a consumer question here, and maybe this has changed since my experience. We have quite a few remote controls and things like that in the house, and I'm always tempted to buy rechargeable batteries, AA's or AAA, rechargeable batteries. And my experience when I've done that in the past is that the alkaline batteries that you just get, from Duracell or Energizer or whatever, work. If we say they're out of 10 to 10, 0 to 10 scale in terms of performance, say they're a 10, the rechargeable versions of those would be maybe a 7. They just don't last as long. Is there a reason why one-time use primary batteries have better performance than secondary batteries or rechargeable batteries?
Oh, yes, because the alkaline batteries actually have more energy density than the nickel metal hydride rechargeables. So a typical AA is going to be 1.5 volts nominal and probably around 1 to 2 amp hours. The way primaries are done, they're not like rechargeables. They don't have a defined amp hour rating. Instead, they have a chart. So if you discharge it at 500 milliamps, this is how many amp hours you get. If you discharge it at 25 milliamps, this is how many amp hours you get, because of the way the internal impedance is. The impedance changes with a load. So it's 1.5 volts, whereas a nickel metal hydride is 1.2 volts per cell. And then your energy density, well, your amp hours are going to be roughly the same. So if you have 1.5 volts at 1 amp hour for a for a alkaline battery, then that's 1.5 watt hours. Whereas it 1.2 volts for a 1 amp hour nickel metal hydride, that's 1.2 watt hours. So you automatically have 0.3 watt hours greater in an alkaline. So they last better. And then at a higher starting voltage, they're a little bit more efficient. So they can run your device a little better. I'll give you an example. On the side, I guess you call me an audiophile. I used to install sound systems and things and live stream systems. And when you have things like wireless microphones, a lot of times cheap rechargeables will not work in wireless microphones because of how bad the voltage sags under load. You have to use alkalines because they hold their voltage so much better under load. So in alkalines, you're starting, usually it's a 2 series. So when you take a battery and put them together in series, the voltage multiplies. So a 2 series would be 1.5 volts times 2 would be 3 volts. Whereas in a nickel metal hydride, it's 2.4 volts. So you're already fighting that battle there. Your voltage is so much lower. So you're missing 600 millivolts there. So that's why nickel metal hydride just hasn't got as great of a starting voltage and then hasn't got as great of a capacity, but it's rechargeable. So, you kind of make that sacrifice, I guess. But in some devices, it does not work.
That might explain why in the professional audio world, when you see like a concert mic or something, that the actual battery part is almost sticking out of the package. It's huge, and because those are all rechargeable, and I guess they have to overcompensate with physically a larger battery to be able to handle that load. How does temperature and environmental factors affect battery performance? And I'm thinking of EVs. That's a great example. That they don't want to be too cold, they don't want to be too hot. The performance is affected on either range of normal temperatures, and I'm not sure if the performance degradation is the same when it's ultra cold versus ultra hot, but I do know it's different. So how does temperature and other environmental factors affect battery performance, and what can designers do to mitigate these effects? Certain things are going to go where they're going to go, right? So if something's going to go downhole in Houston, and maybe a little sensor or something that has to be powered by a battery, and that's hot down there, or it has to go, drill in ice in Antarctica and sense something, and that's another extreme. How do engineers, battery engineers, manage that?
Well, you're in luck because we have customers that do both of those things or close to both of those things. So for extreme heat, we actually have a customer who makes firefighting equipment, and they have battery packs that go into the fires. So that gives you the warm fuzzies, don't it?
Yeah.
But they actually have battery packs that go into the fires, and so there are rules for that. There are standards for that. The biggest one is intrinsically safe. So the battery pack cannot be able to provide an external spark that could ignite hazardous gas. Also, for those type of batteries, we put in a specialized potting compound to where if the battery pack did get too hot and it did vent, that potting compound would absorb the electrolyte and not allow it to catch fire. So in extreme heat environments, we put the battery packs through a lot of specialized testing and a lot of specialized situations in order to make sure that nothing would happen. And then same thing for extreme cold. We used to build a battery pack that had a heat blanket in it, had a little heat pad, about 3 inches by 3 inches maybe. And when you would use the battery, it would leach off some of the power to keep the battery warm during operation in extreme cold environments. We also have some battery packs that go on some asset tracking stuff that go on, shipping containers and trucks and trains and those kind of things. And, they're in sub-zero temperatures when you go up north during the winter. And so those batteries went through specialized testing to make sure they could handle the extreme cold, and then their devices. So you wonder what engineers can do. So the batteries will warm up if you put them under load. So what a lot of our customers do that have extreme cold situations, when the device boots up, it will do a 5-minute warm-up cycle where it will put some kind of nominal load on the battery to warm it up to the point where it can perform. Yeah. Same thing with charge. It would leach charge into it to the point where it would warm up and perform. So there are a lot of ways you can put batteries in extreme environments, but I would highly advise you put whatever your battery packer sells it through that specialized testing to make sure it can handle it. Because some cells in extreme temperature testing did explode. So you need to make sure the cell can handle it.
Why do you think the auto industry is still using lead-acid batteries, 12-volt lead-acid batteries in their cars when there's so much higher tech out there?
Because they're cheap, they're easy to manufacture, and they're safe. So you don't have to treat a lead-acid battery as anything special. It just does what it does. It can be charged at hundreds of amps. In your car with your alternator, you have a 200 amp alternator, 150 amp alternator normally in your car. It can handle that kind of charge. It can handle it that kind of all day long. And then they're very safe. Hardly ever do you see an actual fire caused by a lead acid battery by itself. Normally, I've seen car fires. I actually had one happen. When I was out one day, this lady drove in the front of her truck was smoking. She was driving a little Nissan Frontier, an early 2000s Nissan Frontier. And one of her battery cables had rubbed. Her positive battery cable had rubbed and then had shorted against the body of the truck. Mm-hmm. And so then the lead acid battery started smoking, and then eventually it did burst open and cause a fire. But it wasn't the battery's fault.
Right. That's a short cause fire. That's downstream fire, right?
So that's why you see, like your emergency lights, the emergency lights we have here in the office, they have lead acid batteries in them. They're just cheap to manufacture, and they are just safe. Whereas if you did that with lithium-ion, you would have to have safety circuits and things, and it would have to be specialized tested and all this. We have several customers that we have replaced their lead acid with lithium-iron phosphate. That is a lithium-based chemistry that was made as a drop-in replacement. It's stable, not as volatile as lithium-ion, won't go into thermal runaway, those kind of things, but does have flammable electrolyte. So, some of the customers that we try to work with, they just don't want to leave lead acid because there's no testing behind it. You can just drop it in and it goes. So,
yeah, we've used it since. Well, I guess the early systems were 6-volt batteries, and then they moved to 12. But yeah, we've been using that technology for 150 years, however long cars.
I have a book here. From, I believe this is from 1948 or 1946, Principles and Practice of Electrical Engineering, and it has a whole section on lead acid batteries in it. It's pretty cool.
Yeah, there's a blast from the past there.
I have a whole collection of vintage books back here. Yeah. And vintage radios. I collect vintage things.
Nice. You're still able to get vacuum tubes for those old radios?
Yes, you can still buy surplus vacuum tubes still in the packages and stuff. Now they're expensive. You're better off finding, beat up old radios at yard sales and stuff to steal tubes out of. But
the highlight of my childhood, I think, outside of maybe the holidays or something or birthdays, was when my dad sent me to Radio Shack to test some tubes. The TV wasn't working, something wasn't right. It was one of the tubes needed to be replaced. He didn't know which one, so he just grabbed all the tubes and sent me to Radio Shack, and you went up to the tube tester, and I felt like I was Captain Kirk on the bridge of the Enterprise. That was the most space age thing I got to do. That was I always enjoyed doing that. I would, if I knew how at the time, I would have broken a tube just to be able to go and test it. That was a fun experience. You talked about battery conditioning, and cycling a battery, putting a little load on it to get it to heat up to an optimum temperature. I know that in the Tesla Model S, in the ludicrous mode, which is their insane power mode, if you're going to put it on a track and try and do a quarter mile or whatever in that mode, it actually gives a little countdown because it's conditioning the battery to get ready for that tremendous draw. And another brand of car, I forget which one it was, it's an EV, that had their equivalent of that ludicrous mode, the insane mode or whatever they call it. But they limited the number of times you could do it to, I forget what the number was, it was like 50 or 150 or something like that, for the life of the car. And they said it was to protect it because it's a huge strain on the battery and probably G-forces and, the mechanical components. But it was such a huge strain mainly on the battery that Tesla doesn't care. You can do it as often as you want. But another company said, no, 100 and whatever times, over the life of the car that's it. So unless you hack the software, there's not much you can do about it. What are the most common, we talked about thermal runaways. That's certainly a safety issue. That's the poster child for safety issues. But what are the other, maybe less common, but still common safety issues or failure causes in batteries? It could be safety or just failures. And how can these things be avoided?
Oh, definitely. So shock is a major thing in battery packs. So when you're designing a battery pack, you want to make sure that it can handle external shocks, or so if a battery pack is dropped or if it's slammed against something, batteries they're welded together, and then maybe in a holder, maybe they're glued. But if you don't do it right, the G-forces when it hits, you can break tabs off, break batteries apart and things. And if that happens, then inside of whatever your case is or whatever your device is, the battery breaks loose or comes apart, then it shorts out and causes a major problem. Also, heat is another thing. So we use a lot of they used to be A123, now it's Lithium Works cells. They're very specialized lithium iron phosphate cells that can do 80 or 90 amps a piece. They're really high power cells. But when you're using them, if you use them for an extended period of time, they will heat up. And we're talking, if at max load, we're talking above 100 C kind of heat.
Okay.
So
major
if
heat.
You're not
normal environmental heat. This is like industrial heat.
And that's melt everything in your box heat. So when you have that, that's why EV batteries are liquid cooled, because they heat up so much. So you have to make sure you manage the heat that is created by the battery, because a battery under high load will heat up because of its internal impedance. Well, just like a resistor would, or just like a FET would, a battery pack has internal impedance as well, and so it'll heat up from that power loss internal to the battery pack.
And on the subject of thermal control, thermal management, besides liquid cooling, that's one technique, but what are some of the methods in place to provide thermal management, to prevent a thermal runaway? And how effective are these measures in like high reliability applications?
The easiest method is actually just to put more cells in it. So if you have a battery pack that needs to provide, let's say, 10 amps, and you have one cell that can do 10 amps, then that cell is naturally going to have to work harder versus if you parallel more cells together. So if you have a 4 series pack that's 12 volts and then needs to provide 10 amps, so one cell can do 10 amps. Well, if you parallel 2 cells together, so now you have 8 cells. Each series cell gets a partner, gets a pair. So now that load is shared between 2 cells. So now that's only half the wattage per cell. And so as you parallel those cells together, then the load is shared between them. And so that's how that's just the easiest way to prevent cell a cell from thermally heating up. And then a lot of people will use, a lot of our customers, they'll just use an enclosure and stick a fan on the end. And then the cells are spaced apart, 3 or 4 millimeters in those holders, and then there's just a fan. But normally, the best way to mitigate that is just to stack more cells together.
So no one cell's working overtime.
Mm-hmm.
Yeah. How do regulations play a role? I know that UL is probably in your business. There's IEC, and there's probably others. How do those regulations and standards impact the design and the use of batteries in electronic applications?
So all battery packs have to be tested in the United States to UN 38.3 transportation testing. Now that is not a battery pack safety standard. That is a transportation standard, and that is I'll go ahead and say one of my pet peeves. That is I believe a flaw in the way we do batteries in the United States, because most of your battery fires, if the packs were certified to a higher standard, would not have happened. So take, for instance, New York City. They have passed a law to where all of your e-bike batteries and scooter batteries and things have to be UL listed. All batteries sold, because they had so many fires burning down apartment complexes from bootleg batteries that were untested and being sold on the market, that all batteries now for those categories have to be UL listed. So UN 38.3 is the only thing that's required in the U.S., but it does lack a lot. But IEC 62133, which pretty much everybody in the world has adopted except for the United States as a safety standard, it takes everything to the next level. So IEC 62133 requires that a battery pack have what's called secondary protection. So if the first protection fails, like the FETs we talked about, then there's a backup fuse, or there's another set of backup FETs, or there's a backup or there's FETs to a backup contactor or something like that. There is some secondary protection for the battery pack. It's called single fault. What they do is they'll fault one part of your safety circuit, and then the rest of the circuit still has to handle whatever the safety event is. That's the same for UL 2054. So a lot of medical devices require UL 2054, and it's almost the same as IEC. It's slightly different, but it still has that single fault. So that way your battery pack can protect itself if its primary method of protection does fail. So what we'll do is we'll use what's called a chemical fuse. I don't know if you've ever heard of those, or it's a thermal fuse. So it has a burner in it that can be shorted out. So the smart chip, the BMS chip, can blow that fuse, and then it also acts as a normal fuse too. It can blow with current it can be blown
or temperature.
Yep, it can be blown with current or temperature. And that goes along with the FETs, and that is your secondary device. So if the BMS chip says there's a thermal event or there's a current event, and I've tried to turn off the FETs, and the FETs are not turning off and there's still current flowing or the temperature is still rising, it will blow that fuse. And that is the first, usually you put the fuse as the first thing coming out of the battery pack. So that way, if it blows, it isolates everything. It completely isolates the cell stack from everything. So, unfortunately, UN 38.3 has no requirement like that. In fact, the video clip
your pet peeve, right?
Yeah, the video clip you showed earlier at the beginning, when you're talking about my social media, was a clip from Our Drill Battery Safe, and the requirement isn't even the requirement is fire or disassembly, but leaking of electrolyte is not considered disassembly. So it can even leak out the flammable electrolyte and it still passes as long as it doesn't catch fire. Just it's not. Yeah. It is not a good safety standard. I do not.
Certainly not comprehensive. I view my litmus test for whether something is safe or not by whether or not airlines allow it on board. Remember those hoverboards that were all coming in from China, that you could buy for $30 off Amazon and practically break your neck on them. They were catching fire left, right, and center. The YouTube was, dominated with hoverboard fires and things like that. Because I would imagine, just by nature of their low price and where they were built and who they were sold for, not a lot of safety measures went in. Probably not a lot of standards went into that, and safety standards for the operator or the device itself. and they were catching fire. And I remember being on airplanes saying, you can't have any hoverboards. They asked you if you had drugs or gun, a bomb, lithium batteries in your check bag, or hoverboards on the aircraft. It could not have it. So they seem to be on the leading edge of what's safe and not safe. What are the trade-offs in cost and performance and reliability when selecting a battery for consumer versus industrial electronics? Are there different grades? Oh, I think I'm onto something there. I can tell.
This is a great question. So normally when you're doing consumer electronics, they want the cheapest they can get, right?
Sure.
They want the cheapest cells they can get at no matter the price. So normally the trade-off for that, if you're going to get a cheap cell for a consumer product, is safety. So Moly, Panasonic, LG, Samsung, they make all good quality cells, and there are a lot of others that make good quality cells. However, there are some companies that I'm not sure, what their name is or where they get the materials from, but those are not good quality cells. A lot of times they're just like little lithium cells that have been put in 18650 cases and welded in there. They're not even real 18650 cells. So when you go something like a consumer product, normally you get a lot of performance trade-off because they're trying to make it so cheap. Whereas with an industrial product, they want performance. They want the top of the line performance they can get. They want the most bang for their buck. Now there still is a price consideration there. We have very few customers, they're mostly medical customers, that say we just want the best and we don't care what it costs. We have one or two customers like that. So it's fun as a BMS designer. You get to make the board as complicated as you want, and it just does all these things.
Throw every trick at it. Yeah.
But there's a lot of trade-off when you go to pick consumer grade stuff versus industrial grade stuff. A huge trade-off for safety and reliability. Well, if you buy a cheap consumer device, it'll last maybe a year, maybe less than that, and then you have to go throw it away and get another one. Whereas you buy a good quality industrial device, it lasts for years and years and years. So That is a huge trade-off when you're going to do something like that, a consumer device versus an industrial device.
Let's talk about the end. We talk about selecting the right battery for the application. Let's talk about the end of the battery's life. How important is it to consider battery life cycle and recycling options when it comes to the battery selection process?
It is extremely important. Like I said before, the longer a lithium-ion battery sits on the shelf in a depleted state, the more dangerous it becomes. So a lithium iron phosphate battery, not really. They're pretty safe. It greatly degrades your performance, but you aren't going to see that kind of safety event, neither with nickel metal or like an alkaline battery. But as far as recycling goes, it is very important that you recycle batteries properly, because when they get to the landfill or they get to wherever they're going, if you're just throwing it in the normal trash and one of those cells get punctured, well, that's just going to start a fire, and it's going to cause a huge kind of environmental event. So there is a recycler here in North Carolina where they recycle a lot of metal and things, and one of the local places there in the community had thrown some lithium batteries, some large lithium polymer batteries that go in tablets, thrown them in the regular trash, and it burnt down their recycling facility, burnt it to the ground. Because when they went to grab it, it punctured those cells and just lit everything on fire.
Recently, I remember recently in our town, there was a call from for the fire department to put out a trash truck fire. And, these trash trucks come around once a week, very sophisticated trucks. They have the automatic arm that grabs the can and, dumps it. And then to maximize the number of pickups they can take, every so often it compresses all that big giant trash compactor. And I think somewhere in the fine print when we sign up for garbage service, it says, don't throw batteries away. But, I have to admit, I've thrown double A's in there, which are probably not as problematic as the type we're talking about. But still, people do it. And every once in a while, these trash trucks they combust. And it's really difficult to put that out because lithium in particular burns fierce. And it's amazing.
It burns
how
very hot.
Yeah, and then everything else in there starts catching fire, and it's a sealed unit. They have to basically, and I think the protocol, I watched it happen once. The protocol is when the driver notices all this smoke billowing out of the back of his truck, they empty the truck right there on the street.
Yep, they do.
To save the truck and to also help the firefighters get to the point of the fire. But it's a dramatic event, and so I think recycling is certainly worth thinking about. Does anyone ever change? Maybe they were going to go for battery A, but because of safety and recycling and things like that, if everything else is fairly equal, they'll go with maybe a more environmentally safe or safety-centric alternative to their preferred battery?
Sometimes. So we normally try to talk everyone that comes to us into, if it's large format lithium iron phosphate, because it's easier to recycle. It's a lot safer, not subject to thermal runaway and things like that. But not really if they're, normally if they want a nickel metal pack, they're pretty set on that. But if they want a lithium pack, we normally try to talk them into lithium iron phosphate if it's large format. But most of the time when people come to us, they already have decided what kind of chemistry they want, and then we just go into that. It's hard to, because the different types are so different in their amp hours and their capacities, it's hard to talk them into something different.
Sure. We're about out of time, but I want to do a little shout out to Pro Technologies. Tell me about Pro Technologies, what it does and who it does it for. You don't have to name your top customers or anything, but the types of industries that you do your work for. So the type of work and who you do it for.
What it does is it pays my paycheck, and who's it for is for my family. That's what it does.
Oh, is that your company, Alex?
No.
Okay.
That was just a joke. No.
Well, it does pay your paycheck, and it does pay you to sit here and talk to me. So I'm very grateful to them. Yeah.
But no, we're a custom battery pack manufacturer. Been going since 1986 or 84, I believe, way before I was born. And so they moved here to Pilot Mountain in 96 or 94. And we're a custom battery pack manufacturer. So we do everything. Our boss says we do everything from toilet flushers to defibrillators, which is true. We do battery packs for toilet flushers and defibrillators. And so we're a complete design house. I'm part of the engineering team. We do electrical design, mechanical design, and all of that. And then behind this wall right here is our production facility. We put together packs, weld them, and do all those kind of things. Electrical testing, safety testing, all those kind of things that we handle. And we have a pretty good crew here. I'm happy to work. I've been here for 8 years.
Wow.
I don't know if that's not long enough or too long. The industry changes so much on how long you should work somewhere. I'm not sure where I'm currently at in that line, but I've worked here for 8 years. It's a good place to work. I enjoy it. I enjoy making content here about what I do here. So.
And as we're recording this, it's 4:00. I'm in California, so you're at 7:00, a little past 7:00 there. So you're working late tonight. Is that a usual thing for you?
It is when I'm creating content.
Yeah.
So normally, I work, 8 to 5 every day and get off a little bit on Fridays. But since I've started making content, I'll stay late some days and create content and fool around here in the lab and act like a fool. Those kind of things.
Yeah. Like I think we were talking off camera before we started recording that I do enjoy your style of content. It's you're not one of those that takes themselves too seriously. It's engaging, it's comedic, and it's technically jam-packed full of stuff. But it's easy. It's easily digestible, even though it's technical. I do like that. I wish we had more of that in this industry. This industry can tend to be, like any technical industry, can tend to be a little dry, and I do appreciate the levity that you bring to it.
What I normally tell people is that's what happens when you take an electronics designer off his ADHD medicine.
That's right. That's right. Yeah, that's a good point. Yeah, very good point. Well, for my audience who would like to know more about Pro Technologies, if you're watching this on YouTube, look down here and you'll be able to see a link to Pro Technologies' website and learn more about them. If you're listening to this on your favorite podcast app, go to that podcast app, look at the show notes, and that information will be there as well. Alex Norman, you've answered a lot of questions that I had personally about battery technology, and you've even provided me more information that I didn't even know existed. So thank you for sharing your battery and battery management experience and knowledge with me and my audience. It's been a pleasure.
Well, thank you very much for having me on. I have enjoyed it myself.
Great. Well, thanks again. Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on your favorite podcast app. If you're watching this podcast on the Reliability Matters YouTube channel, be sure to like and subscribe to the podcast to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of every month. And a very special thanks to the Printed Circuit Engineering Association's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks also for your questions and episode suggestions. Please keep them coming. I love to hear from you. Send comments or episode suggestions to Mike at mikeconrad.com. Just remember that's Conrad spelled with a K. To learn more about the podcast, please visit our website at reliabilitymatterspodcast.com. Once again, thanks for listening or watching. Until next time, keep learning, keep doing it right, and remember, reliability matters. I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.